E4B10 says, imagine that two parallel plates having an area of 0.2 meters squared and separated by 0.5 centimeters are given charges of positive 2 microcoulombs and negative 2 microcoulombs respectively. What is the potential difference between the plates? Okay, so let's draw our plates. And we'll say this one's positive. And we'll say the charge here, Q, is equal to 2 microcoulombs, which is equal to 2 times 10 to the minus 6 coulombs. And this is a negative. And Q is equal to a negative 2 microcoulombs. My separation between the plates is S is equal to 0.5 centimeters. And I know the area of my plates, so the area is equal to 0.2 meters squared. So my area would be, if these were to extend back like that, the area would be this area here, or the underneath area. Okay, so the way we're asked to find the potential difference between the plates. So we have phi is our potential, is equal to E, the electric field, times S, the separation between the parallel plates. And so if I think about my parallel plates, my field is going to point this way between the plates. That's going to be my E field. And so phi is equal to E times S. And E, the electric field for a parallel plate capacitor, remember that that is sigma, the surface charge density, over the area times S. I'm sorry, the surface charge density, over epsilon naught times S. And now I know sigma is the surface charge density, and so that's equal to Q over A. So I can plug that in. So phi now is equal to sigma. I'm going to plug in Q over A times epsilon naught, and now I have S on in the numerator. And so when I plug in my numbers, my charge, I can find the charge just on one of the plates, and that's equal to 2 times 10 to the minus 6 coulombs. My separation is 0.005 meters, right? My 0.5 centimeters converts to 0.005 meters. My area, they tell me, is 0.2 meters squared. And my epsilon naught is 9 times 10 to the minus 12 coulomb squared over Newton meter squared. And when I multiply that out, I get 2.8 times 10 to the fourth. And let's figure out our units. So our units, I have coulombs times meters divided by meter squared times coulomb squared over Newton meter squared. Okay, so now I can cross out my meter squared here with my meter squared here. And I'm left with coulombs times meters over coulomb squared here. And now my newtons, since they're on the denominator of my denominator, they come up to the top. So my newtons come up here. And I can cross out one of my coulombs here. And I'm left with Newton meter per coulomb. And a Newton meter is a joule, so I have joule per coulomb, and a joule per coulomb is equal to a volt. So this is equal to volts. So this is my answer for phi.